So solutions can be composed of any combination of phases, two gases, a gas and a liquid, two solids, all different possible combinations. You can even get gases dissolved in solids. How do we determine if a solvent will dissolve a given solute? We know that any particular solvent will not dissolve all possible solutes. Water is a very common solvent, but not everything dissolves in water, which is a really good thing, right? Because what would happen when it rained? Everything would dissolve. You take a shower and you dissolve and go down the drain, but the drain goes down the drain too. Not going to work, right? Everything would just fall apart. So thankfully that's not the case. But when we talk about solubility, we talk about how much of that solute will dissolve in a particular amount of solvent. And so something might dissolve, but only a little bit. Other things may dissolve, and you can get a lot to dissolve. And that solubility depends on this tendency of nature towards mixing and also the types of intermolecular forces. This is an example of gas dissolved in water, soda water. It's got carbon dioxide as the solute in water as the solvent. Many physical systems tend toward lower potential energy. And this can be a bit confusing, but I think the clearest example is you think about a ball rolling down a hill, right? Why does the ball roll down? Because the potential energy is lower as you get closer to the center of the earth. So many physical systems will move in a direction that lowers their potential energy. Well, when we form a solution, when two things mix together, it doesn't necessarily lower the potential energy of those particles. So here we can look at two gases, neon and argon, separated in a container. We take the barrier away, these are going to mix, right? Because gases are going to go in a straight line until they run into something, and so fairly rapidly they are going to mix together. Does that cause their potential energy to be lower? No, it doesn't. So lowering of energy is not the reason why nature likes to mix things. There's got to be something else that's causing that to happen. And that thing is known as entropy. So entropy can be defined lots of different ways, but it's a measure of energy randomization or energy dispersal, energy spread in a given system. So when we have two ideal gases mixing, the kinetic energy of each of those gases gets spread out over a larger volume. And so that causes the entropy to increase, which makes it a favorable process. So here, neon's thermal energy was confined to half of this container, and argon was confined to the other half. Its energy was confined. When we remove the barrier and let them mix, now both neon and argon spread their energy over a greater volume. And that's an increase in entropy, and that's what drives the mixing. So substances mix because of this pervasive tendency for energy to spread out whenever it's not restrained from doing so. Entropy also explains the transfer of thermal energy from hot objects to cold objects. We've learned that heat will move from a hot object to a cold object, but why does it do that? Well, the hot object has more energy, and when it spreads its energy into the cold object, it's dispersing its energy and entropy is increasing. Intermolecular forces are very important in the formation of a solution. They can promote the formation of a solution or they can prevent it. So here's our quick review of the different intermolecular forces we learned about in chapter 12. So here's dispersion force. That happens between all types of molecules and atoms. Dipole-dipole force happens between two polar molecules. Hydrogen bonding is a special kind of dipole-dipole force that happens in polar molecules where ET phone home is true, where you have fluorine, oxygen, or nitrogen directly bonded to a hydrogen. And so here, water and ethanol are examples. And then the last type of force is the ion dipole force, which is between a polar substance and an ion. And so those are the forces that are involved in making or not making solutions. So those intermolecular forces are present between solvent and solute particles, but they're also present between the solvent particles themselves and between the solute particles, right? So we learned this phrase in the last chapter, like dissolves like, which says that if the solute and solvent have similar intermolecular forces, then a solution is more likely to form. And we also learned the word miscible or miscibility. Miscible describes two liquids that are soluble in each other in all proportions. So here in this illustration, we've got interactions between the solvent particles, we've got interactions between the solute particles, and we have interactions between the solvent and the solute. And whether a solution will form depends on the types of those interactions and how strong they are. So when making a solution, you're creating solvent-solute interactions and you're disrupting solvent-solvent and solute-solute interactions. So if the interactions that are being formed are stronger than what's being broken or approximately the same as what's being broken, then a solution will form. But if those solvent-solute interactions are much weaker than the interactions being broken, it's kind of up for grabs. It's going to depend on how different they are. Solution may or may not form. Why would it form if these are weaker? Well, if the gain in entropy makes up for the energy loss, then it'll form. If the gain in entropy doesn't, then it will not form. Okay, all of that is very nice. This is the kind of question you should be able to answer for an exam. Determine whether each compound is soluble in hexane. And what we're looking at here really is just that idea of like dissolves like. So, what is hexane like? What kind of a compound is it? And are these other compounds like hexane or not? When we're talking about like dissolves like, we're talking about polar and nonpolar. So, hexane. What are the elements in hexane? There's carbon and hydrogen. So even if you don't remember that hex means 6 and there's 6 carbons and enough hydrogens to make all the carbons happy, if you just remember that this is a hydrocarbon with carbons and hydrogens, the carbon-hydrogen bond is nonpolar. So these hydrocarbons are also nonpolar because they don't have any polar bonds. Any question?
So if it ends in ane, ine, or ene, it's going to be on the hydrocarbon basis?
Yeah.
Okay.
Ane, ine, or ene. Mm-hmm. So the hexane is nonpolar. So what we're looking for over here, if we find out that any of these are nonpolar is like nonpolar, and that will probably dissolve. Is water polar or nonpolar? Polar. I hope that you just kind of remember that by now. If we look at water has 2 lone pairs on the central atom. Oops, I lost one. So Thursday was a new record, 11 trains. Anyway, so this is why I came up with what I call Mrs. K's rules. He's just going on and on. So, I can't talk and write at the same time. So, the thorough way of determining polarity of a molecule is to draw the Lewis structure, determine the electron geometry and the molecular geometry, and find the dipole moments of the bonds and add them together as vectors, right? That doesn't sound fun. So this is the short version. You may still need to look at the Lewis structure, but most of the things you're going to be asked about are going to be fairly simple. So here's the Lewis structure for water. Does it have lone pairs on the central atom? Yes, it does. Well, in order for it to be nonpolar, both of these things have to be true. No lone pairs on the central atom, and the atoms bonded to the central atom are all the same. So water is polar, not going to dissolve. What about ammonia? Can't always tell just by looking at the chemical formula, because we need to know if there's lone pairs on the central atom. This one has lone pairs. So, also polar. Will it dissolve in hexane? No, it won't. How about propane? Is this polar or nonpolar? This is nonpolar. So all of these bonds are nonpolar. If all the bonds are nonpolar, it doesn't matter what else you've got going on. It's going to be nonpolar. So this one is nonpolar, and so this will dissolve. That'll be soluble. Propane is very much like hexane. Right? They're very similar. How about hydrogen chloride? Polar or nonpolar? Polar. Here, we only have one bond, so there's not a central atom. If the bond is polar, the molecule's polar. And in the absence of table of electronegativities, you just ask yourself, well, are those the same element or different elements? Those are different elements. 95% chance that's polar. So also not going to dissolve. Any questions? Yeah.
So, if you have a diatomic like H2 or any of those, are those polar or non-polar? So there was a question about one of those ones. I thought they were non-polar. But
They are nonpolar.
they're non-polar, okay.
So if you have a diatomic element where you have two atoms of the same element, that bond is going to be nonpolar,
Okay.
right? Because to make a bond polar, one of these atoms has to be more electronegative than the other.
Okay.
Since they're the same, they can't be.
So like it doesn't matter it had what was it, N2 I think, and N2 I thought that one had lone pairs left over, so that's why I was confused.
So N2 is going to have a triple bond, and yeah, there's lone pairs, but because the only bond is between two of the same element, then it's nonpolar.
There's no electric.
Yeah. Right, no electronegativity difference, so it's nonpolar. So all those diatomic elements, those are all nonpolar.
Okay.
Any other questions?